Okay. I want to wrap up SN1 or as much as possible. SN1, SN2. I will put we'll start with E1 on Monday, and I'll put the stuff in the Monday folder for that. Right now, I don't think there is a Monday folder. If there is, it doesn't have anything in it. Let's see. We left off what we want to talk about next, which would be relevant for Monday's practice problems that are due, is we did yesterday, or we did on Wednesday. We took an alkyl halide and reacted it with a negatively charged nucleophile in SN1. So we did that two-step mechanism. So the first step was to break the carbon-halogen bond to form the carbocation and the leaving group, which is going to be a halogen to begin with. And then you take the carbocation and react it with your negatively charged nucleophile to form the final substitution product. So we did basically a two-step mechanism for the SN1 reaction. Now, there's two types of nucleophiles we can use. We can use a negatively charged nucleophile, or we can use a neutral nucleophile. And neutral nucleophiles can only do SN1 reactions because they're not strong enough. So what we want to do is we want to do the mechanism because there's an additional step in here for reacting an alkyl halide with a neutral nucleophile like water. So let's say that we have let's take something like isopropyl chloride and react it with H2O. So when people did this reaction, this led them to the whole idea that this is first order and alkyl halide only, because when they changed the concentration of water, the reaction rate didn't change. So we still will get isopropyl now added to an OH. We'll end up with an H plus and then a Cl minus. And a lot of times the HCl will just combine together. Although if it's in water, it combines, but then it reforms HCl because it dissociates in water. So the mechanism here is going to have an additional step. So we're going to have our isopropyl chloride. We're going to break the carbon-chlorine bond. And we're going to form our secondary carbocation, which is allowed, and our Cl minus. Yes? Because it was an isopropyl chloride. I just wrote it out with the H. Let me take the H away. There. Now it's isopropyl. Still was. I'm just writing it shorthand. So transition state's going to look like what? What bond am I breaking? The carbon-chlorine bond. So that's a dotted line to the chlorine. And my charges, who should have what charge? Chlorine will have a delta minus, carbon will have a delta plus. So there's my transition state for the first step. Exactly like we did on Wednesday. Exactly like we're going to do on Monday. Because an E1 mechanism shares the same first step as SN1. So that's why we're going to do E1 first, and then we'll deal with the more difficult E2 later than Monday. So second step. Second step is to have my isopropyl chloride react with the water. Now, water has two lone pairs. That's what makes it electron rich. It's just not as electron rich as something with a negative charge. It's like middle class rich. So it has lone pairs that it can donate. And the one thing that does not happen is that water does not break up into OH minus and H plus. And you could say, well, wait, in general chemistry, I remember writing water dissociates into OH minus and H plus. Except the equilibrium constant for that is 10 to the minus 14th. Right? That's where our pH scale of 14 is based on. So yes, water does break up into OH minus and H plus, but there's not enough OH minus to react. So the whole water molecule is going to react. So the oxygen is going to donate its pair of electrons to the carbon, to the C plus. And over here, we're going to form a carbon-oxygen bond, except now the oxygen is still attached to the two hydrogens. It has used one lone pair to form the bond, so it still has one lone pair left. The general rule of reactions is the charges on one side have to add up to the charges on the other. So I got a +1 on the left side. I need a +1 on the right side. That +1 has to go on the oxygen. So the formal charge on oxygen, it owns 1, 2, 3, 4, 5. It came with 6, it lost 1, so it now has a +1 charge. Who did it lose the electron to? The carbon. Because if the carbon-oxygen bond were to break amicably, each one would get 1 electron. So it lost formal ownership of one of its electrons to the carbon. That's the donation part. Okay, what would the transition state look like? Again, if I'm writing the transition state, I need to write the bond that's being made or broken. So in this case, the dotted line goes to the oxygen because that's the bond that's being made. And then I need to average my charges. So if I average my charges, what's the carbon going to be? It's going from +1 to 0, so the carbon gets a delta plus. The oxygen's going from 0 to +1. The oxygen gets a delta plus. Okay, so we're writing the transition states like we write transition states. Show the bonds that are made or broken with dotted lines, average out the charges. So you look at that and you say, wow, 2 delta plus charges next to each other? That's not very stable. Well, what is that? This is a transition state. It's the peak. It's not very stable. That's one of the reasons why it's not very stable is because it's got 2 delta positive charges next to each other. So what's happening is the plus charge is being transferred from the carbon to the oxygen as we're making a bond. So this was elementary step 2 of the mechanism. This is now elementary, or that was elementary 1. This is elementary step 2. I'm not done. So when you react a neutral nucleophile, I now have to react that in a 3rd step. The oxygen would like to become 0 in formal charge again. How is that going to happen? I'm going to break an OH bond and give that pair of electrons to the oxygen. So the arrow is going to look like that. The arrow always shows the flow of electrons. And electrons always flow towards the positive charge. I only say that because later on when we have to write these mechanisms, I will see arrows pointed off into nowhere. And it's going to take like a semester and a half to break you of that habit, if I can ever break you of that habit. So the electrons always go towards the oxygen. Okay? So now we could actually think about, well, let's just write the transition state. The transition state is going to have the OH bond breaking. Remember, there's no lone pairs in the transition state. The transition state's like the resonance hybrid, so there's no lone pairs there. So the charges then, well, I should probably complete this. I get my final product, and then I have my H plus. And then my H plus can combine with my Cl minus. So I get back to my oxygen with 2 lone pairs. All right, so then where's the plus charges? The plus charges on oxygen, its average is delta plus. There's a plus charge on hydrogen, so that hydrogen then gets a delta plus charge in the transition state as well. So now the charge is being transferred from oxygen to H plus. Hannah?
Why do you break the bond between OH and step 2 and step 2?
Because now we have the entire nucleophile added. So the oxygen is +1, it doesn't want to be that. H plus is fine as H plus, it always is. So then we'll break the bond. Up here we can't break the water because it just doesn't break apart that easily, right? It's only 10 to the minus 7th concentration of OH minus. That's not enough to make the reaction go. So we have to keep the neutral nucleophile intact. What I will say over and over again is the whole nucleophile adds. Okay, so now we have a third step to this mechanism. So this is typically what happens when you have 3 steps, or when you have a neutral nucleophile, you always have 3 steps. The O plus species is called the oxonium ion. A C plus is called a carbocation, although it also can be called a carbonium ion. And then oxonium ions, there's also the possibility of having, I guess, a nitronium ion. That's the typical term we use. I just prefer carbocation over carbonium ion.
So
Anna?
when you react to neutral nucleophile in an SN1, you'll always have an H plus, right, as a product?
Yes.
Okay.
Yes, you will always have an H plus.
Do you care if we write it as H plus Cl minus, or do you want it to be?
It doesn't matter because remember, these are the elementary steps.
Okay.
When I add up the elementary steps, I get the overall reaction. In this case, you would say, well, the H plus and the Cl minus would combine, but if this is water as a solvent, it's dissociated because HCl is a strong acid. So in this case, that would be fine. We're going to get to a point where we probably will do the first step in the mechanism and then have the water come in and add to this, so it's one long mechanism. And you can do that if you'd like. You can write one entire step-by-step-by-step mechanism. But I'm showing you the 3 distinctive steps.
I just feel like I'm unsure of how to approach the mechanism, and how to go through it. How do you know where to start?
Well, so what we need to do is we need to know what the 2 we only have 2 mechanisms right now. We got SN2 and SN1. So for an SN1 mechanism, you're always going to start by breaking the carbon-chlorine bond and forming the carbocation. And then you're always going to continue that by adding the nucleophile. If you add a negative nucleophile, it's going to come in and add, +1, -1, come together, neutral molecule, you're done. When it's a neutral nucleophile, it's going to add, so you're going to end up with a C+, then the neutral nucleophile is going to add to that to make the O+, and then you lose the H+ to give you the final product.
So does your final product always have to be neutral?
Yes, your final product always has to be neutral.
I think I'm confused on whether or not this is the final answer. What is the final major product?
Those 2. These 2 are my final product. So the final product is this, and then plus H plus Cl minus. Those are my final products. And that's a good question because, so what's everything else? Well, I formed a carbocation here, right? And what did I do with it? I reacted it. And then I formed an oxonium ion over here, and what did I do? I reacted it. So that's the definition of the intermediate. The intermediates are species that are formed in one step of the mechanism and reacted in the other step of the mechanism, and they cancel out so they don't show up in the overall reaction. So adding up these three steps gives me the overall reaction. So everything in a square is an intermediate. So this mechanism is slightly different because it's got two intermediates, a C plus and an O plus. And it has three transition states because every one of these reactions needs a transition state. So just writing its reaction coordinate diagram, you would have transition state, carbocation, transition state, oxonium ion, transition state, final product. This is your C plus, this is your O plus. So it is a triple humped energy diagram. Three transition states, two intermediates.
Is each hump lower than the last one? Or
Well, the rule is, so what's the rate determining step here? The rate determining step is still step number one. So the rules of kinetics say that the activation energy, it's the biggest activation energy is what's going to give you, is going to be the rate determining step. So no matter whichever way I do this, my first my first activation energy has to be the highest. I never draw these things to accuracy or scale. So if the middle hump is a little bit bigger than the other hump, the key thing is it's a hump, not necessarily its exact energies.
How do we know in this case that it's not like a methyl shift?
Let's forget about shifts for the moment. Okay? I think next week we'll talk about shifts. And the generic answer to that is that I have to tell you when to shift. I will tell you when you do shifts, and for those of you who are like, what's that? We'll get to it next week. I'll tell you when to shift, because the problem is they're introducing shifts now. I usually wait at least a week to a month to talk about shifts, because those are going to just confuse the out of this. They're just going to be really confusing. So we'll hold off on shifts until we get through E1. Then we can talk about shifts. But the rule is I have to tell you when to shift, because otherwise things are going to get chaotic. And I'll remind you of that in next week or so. So right now, the carbocation is formed by the leaving group leaving, and that's it.
Sorry. Okay. So, on the homework it asks about make sure that you put in the wedge and dash lines.
And you wouldn't have to do that for this one, because it didn't start out with a bold and dashed wedge. That's strictly for the cases where I'm going to react a nucleophile with an SN2. Now, if it's an SN1, and I didn't do this with the homework. The homework problem, if I remember correctly, is something like this. It's got like a Cl or a Br there, and then it's got a methyl or ethyl group here. I didn't put bold or dashed wedges. And the reason I didn't put bold or dashed wedges there is because that's not a chiral carbon. Right? That would take us a while back, but that's not a chiral carbon, so bold and dashed wedges don't tell me anything.
so that it's just the Cl and the...
I'll give you the first step. You break the carbon-chlorine bond, and that leaves a carbocation on the tertiary carbon. So you always break the carbon-halogen bond.
So can we like leave like the steps like in that shape? Because I know the book will switch back and forth between like writing the the shape and just having like the CH2 CH3s. Like instead of I don't know, just it's weird.
Like whether it's like that or whether it's like that, it makes no difference to me. So I mean, yeah, we could either leave it there or we could put the methyl group in, just to emphasize the fact that there's a methyl group there. So I mean, you could do this way. So I didn't give you a chiral center to work with. If I did give you a chiral center on an SN1 reaction, remember the lobes are above and below the plane. So in one case, the chlorine would be adding with a bold wedge, and in another case it would be the dashed wedge. That would give us our 50-50 racemic mixture that we get. For SN2, the mechanism always has arrow from nucleophile to carbon, arrow from carbon to leaving group, transition state always being dotted line to carbon, dotted line to leaving group, and then our three other positions in the trigonal bipyramidal geometry, always bold dashed wedge, and then a delta minus on the nucleophile, a delta minus on the leaving group, although that'll change in the future. It may not always be that way. But that's going to be always the transition state we have. So in terms of starting out, is it SN1? Is it SN2? So for the problems for Monday, the first one is SN2, and the second one is SN1. We know the second one is SN1 because it's a tertiary halide. And tertiary halides can only undergo SN1. Right? Why? There's too much steric hindrance for SN2. So that's why tertiaries cannot undergo SN2. Primaries cannot undergo SN1 because SN1 has to go through what kind of intermediate? Carbocation. Are primary carbocations stable? Not in this class. Right, they say that's rule number 3 of what not to do in organic chemistry. Don't take it. 5 bonds to a carbon, primary carbocations. Things not to do in organic. 7 more and I have a t-shirt. I could have a 5 t-shirt, but I can never get past 3. So that's how we know how to start. If it's SN1, break the carbon-halogen bond, make the carbocation, then add the nucleophile. If it's a negative nucleophile, it's 1 step. If it's a neutral nucleophile, it's going to be 2 steps. Now, I've given you an alcohol to react in your mechanism for Monday. And if you're looking at that, it's an alcohol. How am I going to do that? Exactly the same way that we just did it. The difference between HOH and ROH is an R for an H. So if I took this mechanism, if I wanted to react isopropyl chloride with methanol, I would go through this mechanism and I would erase 1 hydrogen and add a methyl group to it. So I would add a methyl group maybe here. Or then I would add my methyl group here, and then I would have my methyl group here. And then I would have my methyl group here because if it's a choice between losing an alkyl group as a plus charge And losing his H is a plus charge. H plus is always going to be lost. Because if I try and lose a CH3 plus is worse than a primary carbocation. So that's what we... So the mechanism is identical. It's just, it's ROH instead of HOH. And I'm not mocking here saying, oh, this is all you do. That's honestly all you do. Is just replace the H with an R group.
Did you pick CH3 arbitrarily for the R?
Yeah, I could have picked CH3, CH2. I could have made it a methyl group, an ethyl group, a propyl group. And in that case, it's the same alkyl group throughout.
So you're saying you'd rather lose the H than the CH3?
Absolutely. Because if a primary carbocation is bad, a CH3 is a methyl, it's not even primary. Right? It has no alkyl groups to stabilize that plus charge. So it is the most unstable. And we should probably, we talked about leaving group ability. Technically, that's kind of a leaving group. It's just if you're going to split a molecule apart and make something super unstable, that reaction is not going to occur. So given H plus versus CH3 plus, it's H plus every day. You're going to lose that. Okay. So basically, this mechanism is what you're going to write for the practice problems. Only you're going to do it with that chloromethyl cyclohexane. So that's what we didn't do on Wednesday that I did with the morning class. Okay. Everybody okay with that? We'll find out on Monday. We might find out over the weekend with questions, but that's what you're going to do. The first one is SN2, the second one is SN1. And there are practice problems in Wednesday's folder. I think they're duplicated into today's folder as well, where it's asking you to do mechanisms. And if there's not a narrated answer key, there's an answer key that goes with it with all the steps. Okay. All right, so we have to be able to write a mechanism for SN2, SN1. We need to know our characteristics. Okay. All right. Any questions about any of the SN1, SN2? Because then I have questions. Here's my question. I have two reactions here, A and B. And I would like to know which one of these two reactions occurs faster. A or B, or C, they react at the same rate, or D, don't know. So which of these two reactions, A or B, reacts faster? Or do they react at the same rate? Or, don't know. I'll give you a minute to think, discuss, and then we'll vote. I do. At some point, since the numbers are getting lower and lower, does anybody have a number 40? You have a number 40? Does anybody have a number 39?
I do.
Does anybody have a number? Well, everybody's probably going to have a number 32. Anybody have 32? No? Anybody have a 33? Anybody have 34? No 34s? How about a 35? How about a 36? How about a 37? Are we back to where we were? 37. The only reason is because if there's two 40s, whoever's 40 I pass through the second time is the one that it counts for. It doesn't matter because only you know how you voted, so. But, okay. Another minute. Which one's faster, A, B, or they go at the same rate?
But also, what is that term?
Okay, are we ready to vote? We might as well at least get a first vote in place. Okay, so A, B, C, or D? Let's see. Hannah, you have to turn yours a little bit more. There we go. Okay, we've got 22 Bs. We've got 2 As, 2 sames, and 1 don't know. Okay, now when we're answering these kinds of problems, the first thing we need to do is identify the mechanism. And I cannot give you 2 reactions that have 2 different mechanisms. They have to be the same mechanism for us to judge their rates. For example, in 2 weeks in lab, we are going to do an SN2 reaction where we are going to boil the solution called refluxing for 45 minutes. If I did that reaction by SN1, I would put in a centrifuge tube, I would add acid to it, I'd cap it, shake it, and the reaction would be over. So while you think an SN1 reaction having 2 steps might be longer than an SN2 reaction, you can't compare. It's like apples and hand grenades. They're not the same. Okay? They're not even close. So whatever this mechanism is, it has to be for both of them. In this case, what's the mechanism for these 2 reactions? SN2. That's an SN2 mechanism. How do I know that?
Because you have a strong nucleophile in both cases, and you have a primary carbon.
Got a primary carbon. So primary alkyl halides can only undergo SN2. Tertiaries can only undergo SN3. Secondaries, it's going to depend, and we may need to refresh and talk a little bit about secondaries. So in examples I'm going to give you, I'm going to only give you primaries and tertiaries right now. And then we'll come back to secondaries. Okay, I've got an SN2 mechanism. That's the first question I ask, SN2 mechanism. Second question, what's different about the 2 reactions? Their leaving groups. Third question would be, does leaving group ability play a role in determining the rate? And the answer is yes, because the rate determining step for an SN2 reaction is alkyl halide times concentration of nucleophile to the first. The rate for an SN1 reaction is K times concentration of alkyl halide to the first. The leaving group is the X in this case. It's in both rate equations. It's in both rate determining steps. the leaving group does play a role. That role is going to be the better the leaving group, the blank the reaction. The faster the reaction. So the better the leaving group, the faster the reaction. So now I ask the million-dollar question, which is, which one of those two is a better leaving group? Chloride or iodide? Iodide? We all in agreement that it's iodide? I forget. Why is it iodide? What was the low rumbling answer that I could barely hear? It's a better leaving group. Well, yeah, it's a better leaving group, but why? Why is it a better leaving group? I don't think so either. Why is it a better leaving group? Sabrina? Okay. Who else was going to say polarizability? You were you going to say polarizability? Annie, what were you going to say?
I was going to say that it's less base. I is lower on the reactors and basicity is decreased.
Okay, so we got two things here. We got polarizability and basicity. And that's okay because that comes up. So our question is, what makes a good leaving group? Leaving group ability is based on one thing. And that is basicity. Leaving group ability is based on basicity. Okay. So of F, Cl, Br, and I, who is the, well, let's see, it's based on basicity, but how? It's
Decrease as it goes down, decrease. It's inversely.
It's inversely related. So in other words, the best leaving group is the weakest base. So of F minus and I minus, who's the weakest base? I minus? Okay, we don't like that question. I'll ask you this one. Of HF, HCl, HBr, HI, who is the strongest acid? Okay, we need a vote. Who is the strongest acid? HF, HCl, HBr, HI? Strongest acid. HF to HI. I got 11 HFs. I got 7 HCLs. I've got 2 HBRs, and I've got 10 HIs. Now, in terms of rules of multiple choice test taking, we could probably eliminate this down to 2 possibilities, right? The top or the bottom. Although sometimes it could be in the middle. In this case, it's either HF or HI. HF. When I put HF in water, do I get complete dissociation or do I get an equilibrium? I get an equilibrium. When I put HI into water, what happens? Complete dissociation. So HI is the strongest acid, making its conjugate base the weakest. So I minus is the weakest base. And so I minus is the best leaving group because it is the weakest base. Now, where does polarizability fit into this? Because when I asked the question this morning, I heard the same thing, polarizability. So what was polarizability? Polarizability came into play when we talked about what makes the strongest nucleophile. So when we talk about nucleophilicity, what are we talking about? Horizontally, if it's a horizontal relationship, the best nucleophile is the strongest base. Okay. Horizontally, it's going to be the strongest base. But when we go down the periodic table, what happened? Polarizability took over, and so what is I minus? It's the strongest nucleophile because it is the most polarizable, and I even heard squishy during the discussion. So that led us to say that I minus was the best nucleophile, but because of polarizability, it is also the best nucleophile of the halogens. So it is not only the best leaving group, it is also the best nucleophile of the halogens.
What is like stability related to? Because like if it has a resonance structure, is that for the leaving group?
That's for the carbocation. Well, that was for the leaving group. And the stability, like when we said, well, if I have an O minus with an S double bond O with the R group, if I had that as a leaving group, it's really good. It was because this was really stable. And how do I make something a really lousy base? By making its conjugate base really stable. So resonance came into effect with stability. That caused the equilibrium to shift to the right, causing the HA to become stronger, causing the A minus to become weaker.
So the quality of the leaving group is based on basicity and stability?
That's it. Stop. Basicity. But stability can make something weaker as a base. Because the chemical principle is the more stable you are, the less reactive you are. And so something that's really stable is not going to be as reactive as a base.
So when you're comparing, like, when you're going horizontally, so like O to Cl, which one is, like, how does that, can you compare those?
So if I went CNOF and then Cl, Br, and I, in terms of nucleophilicity, everything here beats anything here. So these are always stronger nucleophiles than these ones. So an O minus beats all the halogens. And an N minus beats the O minus and all the halogens. So anything that's not a halogen is stronger than a halogen. But it's only in the halogen area do we have this idea of polarizability. Well, polarizability also, sulfur is a stronger nucleophile than oxygen is. Because sulfur's below oxygen on the periodic table, so it's more polarizable. Sabrina.
So when you're talking about horizontally, but the best leaving group, how is that? Like, what is the best leaving group out of this?
CNOF, F.
So it's kind of the opposite, so like the FCL, BRI are better leaving groups than the CN and O, or do you know? Or would you not compare
Yes.
those? Okay.
F minus F, Cl, Br, and I are going to be better leaving groups than an O, N, and C. And we're going to talk about that because basically an OH does not leave. Because for an OH to leave, it'd have to leave as a hydroxide. That's what we consider to be a strong base. Strong bases don't leave. Unless we do something special to them, which we'll get to. Okay.
So what if we were comparing the reaction rate of like the resonance structure one and then compared to like I? How would you know which one?
I would have to tell you that I think this beats every halogen, and it beats I. But I would have to tell you that, which I just did. So this leaving group is a super hot leaving group that will leave. And it will be better than any halogen. But I'm probably not going to ask you that one right now. Because there's a whole series of compounds that we'll learn about maybe next semester that are based on that structure. Again, this is a place where Top Hat is foreshadowing stuff that's going to happen months from now. That when we get to that, I could go, oh, remember we talked about that, and then move on. And then everybody would be like, no, I don't remember that. So it's better for me to just talk about it then than talk about it now. But there were some homework problems. And I even talked about this in a Piazza question video. I do remember doing that. Okay. All right. We haven't answered this problem yet, have we? So what were we at? SN2, leaving group. Leaving group plays a role. Which is the better leaving group? Iodine's a better leaving group. So which reaction goes faster? B. Although given these results over here, they may not correlate to 22 getting that one right, the basics as we break it down, okay? So leaving group ability, and it does play a role. Okay. Let me ask you one more question about these rates. Are we okay with this? The question I asked this morning was I put the same leaving group on there, but I had an OH minus versus an F minus. So it was the nucleophile strength. Or wait, no, that's this problem. That's this problem. There we go. So reaction A and B and C is the same. So of these two reactions, which one do you think is faster, or do they have the same rate? Whenever you're ready to vote, you can put your card up. Bless you. Everybody ready to give their answer? We have 9 A's. We have 17 B's. We have 4 sames. Okay? Let's go through again quickly. Mechanism. SN1. What is different about these two reactions? Nucleophile strength. Who is the stronger nucleophile, F minus or OH minus? Okay, let's move on to the next question. Does the nucleophile strength matter? Wait, what are all these sighing O's about? Are you just as confused as I am as to I'm not confused. What's the rate equation for an SN1? Does the nucleophile strength matter? No. the nucleophile doesn't show up in the rate determining step, it is not part of the rate equation. So in this case, they're going to be the same. They're going to be the same rate. But I'm still not comfortable with the idea that which one is more a stronger nucleophile, F minus or OH minus. OH minus, we agree on that? So on our periodic table, basicity moves from right to left. C minus stronger, N minus stronger than O minus, stronger than F minus. So that would make the O minus a stronger nucleophile than F minus. So in this case, yes, OH minus is the stronger nucleophile, but it doesn't matter because it's an SN1 reaction. Okay? All right, we'll talk more about these kinds of things. Solvent effects, I can ask the question about that. But on Monday we'll go into E1, and then we can come back and talk about any questions you have here. Put them on Piazza. Any questions? Email me, and your problems I will pick up on Monday. So if you have any questions about those, you could email me as well.